So as people are just joining, as I said a minute ago, it's a new COMET webinar team, so we just apologise if anything goes a bit wrong here. We're just learning as we go. I'll kind of introduce us here. So we've got Ben and Jen and myself. If anyone has any requests on who they would like to see, either COMET or COMET Plus members give a little talk, then please just reach out to us. Today, I'll probably just kind of start now. Today, we have one of my colleagues from the British Geological Survey, Ekbal Hussain, and he's going to give a really kind of different perspective talk to the usual sorts of very heavy science talks we have in COMET webinars. So Ekbal is a multi-hazard and remote sensing geoscientist at BGS. His research focuses on satellite data to understand natural and anthropogenic hazards such as earthquakes, landslides, subsidence. He's worked with partners in Indonesia, Turkey, Ethiopia, Vietnam, to name a few. In addition to hazard and risk science, he works with stakeholders to understand and manage disaster risk. So in Indonesia, he has engaged across national and local agencies to develop contingency plans for both earthquakes and response mechanisms for effective hazard risk management. He's a PI on the UK's sponsorship for the Global Earthquake Model, so the GEM model, and he is a member of the NERC Science and Innovation Advisory Committee, which advises NERC on strategic science priorities and funding allocations. So as we'll just fly straight into Ekbal, you can take it away for us. And again, any questions, pop them in the Q&A and we'll deal with them after Ekbal's given the talk.
Right, thanks, Erin. Thanks all for inviting me to talk to you all. And it's great to be, here with everyone. And as you all, some of you may know, I've been part of COMET since the very early days of my research career, since I was a PhD student. So thank you all for coming along to listen to this talk. And so I want to talk again, as Erin said, something slightly different. It's mostly around this bigger issue of hazards and disasters and how and why natural hazards turn into disasters. And I'll use the hazard I know best, earthquakes, but please keep in mind as I talk through this lecture on that the themes I'm going to talk about apply to all hazards, whether natural, such as earthquakes, volcanoes, tsunamis, landslides, etc., and anthropogenic, whether it's technological hazards or subsidence and things like that. So, but I'll use earthquakes to demonstrate the core principles. And I'll use one particular area that I know very well to demonstrate some of these ideas. So this is Turkey, and this is the GPS field in Turkey and the surrounding area. You will have seen figures like this throughout the many other COMET lectures you've had over the last few years. But just quite simply, Turkey has this wonderful anti-clockwise rotation that's triggered by or responding to these two big forces: Arabia, a big continental mass punching north into Asia around 15 millimeter spear, and the Hellenic subductionism, which kind of pulls the Turkey. And what happens is Turkey moves to the west and rotates along these two main fault structures: on the north, the North Anatolian Fault, and in the east Anatolian Fault. And that's the main sort of geodetic tectonic setting of this particular area. And just quickly look at the North Anatolian Fault. Over the last century or so, the fault has had a series of very large and interesting earthquakes. In 1939, there was a magnitude 7.8 earthquake here, the Erzincan earthquake that killed around 30,000 people. 2 years later, there was an earthquake here, significant size again. A year after that, a magnitude 7.7 here. And a year after that again, a 6.8 there. Decade after that, a 6.8. Decade again, magnitude 7, and then a couple of decades later, 2 large 7s here, and a small earthquake in 2022 here. And so it doesn't take a genius to spot the pattern, right? The pattern's from east to west. The earthquakes are unzipping along the North Anatolian Fault. And again, it doesn't take a genius to think where the next one could happen. What we've all been looking out for was this gap here in the Marmara Sea. And the problem here is that's Istanbul, one of the largest cities in the world, around 15 million people. And that's where that next big earthquake probably is going to happen next. So our eyes were all on there, waiting for that thing to happen, that disaster that we knew was possible. What happened in February 2023? That one ruptured at the East Anatolian Fault, which is a fault that we've known about for a long time. It's been dangerous and it has been collecting energy, straining. But those earthquakes caused us out. And what happened in those earthquakes? Two large earthquakes, a magnitude 7.8 at 4:17 in the morning, local time. That time is important. I'll come back to that later. And something like 9 hours later, at 1 o'clock in the afternoon, the second magnitude 7.5 earthquake up here to the west. And these are the kind of things that happened, big buildings that got completely destroyed. Some statistics, nearly 60,000 people were killed in this earthquake, 54,000 in Turkey, and around 6 to 8,000 in northern Syria. The population of some of these towns, Kahramanmaraş, Hatay, and Adiyaman, were decimated, some of them up to nearly 50% of the population in some of these areas. Over 250,000 buildings were damaged or destroyed in both countries together, and direct economic losses of around 160 billion US dollars. Remember, that's the direct economic loss. That doesn't count for the years of recovery needed and the lost income of the rest of the preceding years. So in every measure, this was a disaster of pretty significant scale. And so what did the scientific community do? How did we respond to that? So this is what COMET did. COMET produced these amazing interferograms and pixel offset maps that really mapped the detail of where the deformation was focused and which faults exactly ruptured. And this is quite important because the early fieldwork helped, these sort of maps early helped target the early fieldwork activities and identify where we needed to go to really target the fieldwork surveys. And so, as you all know, because you're part of COMET, and we can make these kind of measurements now within a few days of almost any earthquake, almost anywhere in the world. And so once you have that data, you can do these things like this, the slip inversion models that, again, you will have seen. This is the slip inversion model by Sylvain Barbeau of that main magnitude 7.8 earthquake. And it shows the fault slip from the south here to the north up on the bottom right. And, most of that fault slipped with varying levels of fault movement. And the maximum was around 5 to 10 kilometers deep, with a maximum slip of around 8 to 10 meters at depth. But it helps. So this kind of inversions help us map where the fault moved, and importantly, where it didn't move. So this was identified by these guys as a seismic gap. And in fact, the year later, so 2024, there was another smaller 6-point-something earthquake, which filled in this seismic gap. So, this kind of analysis helps us understand where the strain energy was released, but also importantly, where it was not released. So for seismic hazard and some has forecasting and this assessment of future risk, this kind of information is very helpful. So we can also combine all this information. So that was what happened during the earthquake, but we can also combine information from things in the interseismic period. So these are profiles of interseismic velocities and slip rates. And then we could do scenarios, run earthquake simulations to estimate, the shaking intensities and potential losses. But all of that, all of this deformation helps us produce these kind of hazard products. So knowing the deformation now and in the past helps us to produce better hazard products. So, i.e., we get better understanding how dangerous this fault is. However, this is the seismic hazard map for Turkey. This was produced in 2018, following decades of research on seismic, understanding where the seismicity is, the strain rates from geodesy, etc. And in this map, and they put it all together into this what we call the probabilistic seismic hazard model, and it shows where it was dangerous, basically. The red faults, the red lines are the big faults, the north and eastern antenna fault, and red is dangerous. The probability of having high intensity shaking in the area is quite high. And as you can see, these fault lines, even the Chardak segment that ruptured in the second earthquake, these were all already identified as pretty dangerous. They were straining and they had high seismic hazard potential. So why did 60,000 people die? If we knew it was dangerous, and we've known it was dangerous for a long time, why did 60,000 people die? And so knowing the hazard, the geophysics, is not enough to manage disaster risk. There's more at play here that turned that hazard and all that knowledge and made it basically not very helpful in the event of the earthquake. So that's what I really want to get into the detail of how knowing the hazard wasn't enough to manage, understand the risk. So to do that, I'll step out a little bit and look at the more global picture. This is a figure from Roger Bilham's, one of Roger Bilham's papers, that shows an earthquake magnitude against total fatalities in those earthquakes. And let's make a simple assumption: large earthquakes kill more people. And if you follow this sort of gray zone, you can see there is a tendency for large earthquakes to have more fatalities, i.e., there's a positive correlation. But is it so simple? And I'll illustrate that with a couple of examples. Here is the Turkey earthquake in 2023, a magnitude 7.8, killed around 60,000 people. So more or less falls within this predicted trend. Here's the largest earthquake we've ever measured in 1960, a magnitude 9.5. So far, it's off the scale. That killed around 3,000 people. So I mean, that's still a lot of people. But if you were going by this trend, it should have been up to about 1 million deaths. Here's the Haiti earthquake in 2010, killed potentially the most fatal earthquakes in the last 20, 30 years or so. And it killed, as a magnitude 7.1, killed around 100 to 300,000 people, depending on which data source you use. And year after that, in Pakistan, the Dalbandin earthquake, again, a magnitude 7.1, killed around 3 people. So, the same size earthquake in Haiti killed 100,000, and in Pakistan killed 3. So there's clearly more to this story than just size. It's not just size that matters. And this is really where I want to get at, how and why natural hazards lead to disasters. And this is the answer. I'm going to start by giving you the answers: exposure, vulnerability, corruption, and ignorance. And what do I mean by these? Exposure is, where are the things that we care about? And what are they? What are the things we care about, and where are they? Vulnerability is, how fragile are the things that we care about? Corruption is, how enforced are the safety regulations? We're not even questioning that the safety regulations don't exist, because almost every country has regulations. Ignorance, does everyone know what the regulations are? And for the next part of this talk, I'll go over each of these in a little bit more detail. And because I couldn't resist the temptation, I've called these the 4 horsemen of disaster risk. So these are my 4 horsemen. And so we'll start with horseman 1, exposure. And exposure for earthquakes is a question of 2 parts. Where do people live, and what sort of buildings do they live in? So the first part of that question is actually quite easy. We know where people live. Almost every country in the world has a census survey, and we can supplement that with satellite imagery and other sort of auxiliary data sets to build a really detailed map of where everyone is in the world. And this is where they are. This is the global population mapped onto a map, and it's pretty clear that the population density is unevenly distributed around the world. And that's a simple but a very important observation. There's a whole band of high population density going from Europe all the way through the Middle East, South Asia, and East Asia. And that matters because that's all about exposure, where people live. What kind of buildings they live in is a harder question, and because it clearly matters in an earthquake if you're living in that top building versus the bottom building. And this is a much harder nut to crack, because to do a proper exposure assessment, you'd have to go to every building in the world and do an engineering survey of that building. And that turns out to be much harder. And this remains one of the biggest challenges, to get a proper exposure model that has with it the fragilities of that building. There are some clever approaches now to sort of address this gap, but it still is one of the big challenges in sort of earthquake risks science. And here's a map. This is quite an old map, so sorry it's grainy. It's from Roger Bilham's paper again. And of all the fatal earthquakes around the world in the last century or so. And the larger this box, the more fatal earthquakes have been in that box, or fatal the earthquake, the more fatal the earthquake. And if I plot on here the subduction zones, you're all geologists, you should know where they are. This is where you get the biggest earthquakes, right? The magnitude 9s, the high 8s, they produce tsunamis. This is where you should think are the most dangerous places to be in an earthquake. However, in that red circle is where most people die in earthquakes, where you don't get the very, very large earthquakes, but it's actually where most people are concentrated. So 85% of all the world's fatal earthquakes happened in that red circle in the last 1,000 years, not actually along the subduction zones where you think they get the biggest earthquakes. So some countries have a higher exposure to earthquake risk than others. And most fatalities happen in earthquakes between magnitude 7 and 8, in earthquakes in the continental interiors, mostly because that's where most people are as an exposure I think. And that's a statistic from, I should have cited it, James Jackson's paper from 2011. Vulnerability, horseman number 2. And this is actually my favorite graph, and I'll try and explain it step by step. So what do we mean by vulnerability? It's the physical or social conditions that increases the risk, increases the susceptibility to hazards. And so let's start with the social first. So this, quite clearly, is the world's population from 1820 to about 2020 now. The population went up from about 1 billion to just over 8 billion right now. And again, this is not a surprise to anyone. Population has gone up. This is the number of people who have lived in extreme poverty in that same period of time. And again, this is something that's really well defined. It's anyone who lives on less than 2.1 international dollars a day. That's just about enough money to feed yourself on a daily basis. So every single person in red there, nearly a billion in 1820, up to 2 billion in 1960, could not feed themselves on a daily basis. And if I turn that into a percentage, so the number of people, fraction of people live in extreme poverty, it looks like that. So in 1820, 80% of the world could not feed itself on a daily basis. And that proportion has gone down nearly systematically down to around 0.9% now. So this is probably one of the best and good news stories that isn't as well known as it should be. I think this is a statistic we should all be proud of as an international citizen. That we managed to bring down extreme poverty to the levels now it has. So much so that all the world's media could have ran this headline: 115,000 people escaped from extreme poverty since yesterday. All the world's media could have run that headline every single day for the past 35 years. That's how many people come out of extreme poverty. So that's a good thing. This is a really good news story. So why is it one of the horsemen of disaster risk? It's because extreme poverty looks like this. In most people who are extremely poor live in homes that are locally built, made with local materials, usually wood or bamboo and things like that. And these kind of buildings are actually quite resilient to earthquake shaking, and because it can absorb energy and it can sway, and even if the roof falls on you, it's unlikely to kill you. But when people come out of extreme poverty, remember, they're still extremely poor by any measure, in any Western measure, they're extremely poor. But they do 5 things when they come out of extreme poverty. And they arguably come out of extreme poverty because they do these 5 things. They send their kids to school. They vaccinate their children. They get a mobile phone. They get electricity. I have no idea how people get phones before electricity, but that is the case. And then they build their own homes. And remember, so these people are extremely poor, so they can't afford an architect, an engineer, or anything like that. They build their homes themselves. And this is exactly the kind of homes they build. This is a photo I took in Bangladesh, where this family who lives in this tin and mud house in the background have come out of extreme poverty, and the owner is building his own house here. With no sort of formal training in masonry and design and architecture or anything like that. It's just 4 walls and a roof he's building. And remember, they're still poor, so they need to use the least amount of materials they can get away with to build their homes. And if you notice, these bricks, they're side-on, flat side. If you go outside and look at the wall, the bricks are flat. And they're flat because it increases the surface area of the wall with the ground. It just gives that extra stability. But if you build your wall with flat bricks, you need more bricks, and that's more expensive. So if you don't have much money, you build the bricks, put the bricks side on. But that fundamentally weakens that wall, and it doesn't provide that sort of stability it needs, especially when things start moving. Here's another example. This family have moved out to this bamboo and tin house on the left to this house on the right, where it's same idea, brick side on. The pillars, the strength of a house is in its pillars, and the strength of the pillar is the number of rebar rods, metal rods you put in those pillars. And these pillars don't have enough rods in them. It's very thin. And actually, in an earthquake, you'd be safer in the tin house than you'd be in this house. So it's a sign of economic progress, but it's increased their risk of vulnerability, I should say, to the shaking when it does happen. So what do we say? The jump from extremely poor to poor often increases the risk to earthquake shaking. Not always, but often increases the risk because of this issue with homes. And this is, again, conforms to this age-old a comment from Nicholas Ambrosius that says earthquakes don't kill people, buildings do. And so that's physical vulnerability. So social vulnerability is another aspect that we need to consider. Let's go back to Turkey, the earthquake in 2023. Before that earthquake, this is the map of annual disposable income in Turkey. So red colors are areas of Turkey that have high disposable income, i.e. they are wealthier, and pale colors are areas of Turkey that are poorer. They don't have high disposable income. And blue is a sort of quick mark of where that main earthquake was, i.e. in areas that are relatively poorer than not. In fact, 1.5 million people lived below the national poverty line in the 10 most affected provinces in Southeast Turkey by that earthquake. Here's another measure of vulnerability. So this is one of my favorite statistics, and I have an entire lecture on this statistic alone that if you want to hear for another time. But in briefly, it's the total fertility rate. And what we mean by fertility rate is the number of children a woman or a family chooses to have. And you'd think, why would that measure against vulnerability? It's because the number of children on average a family chooses to have has nothing to do with their religion, their race, their ethnicity, their geography, which country they live in. It has nothing to do with that. It only correlates with one measure. It correlates with poverty. So larger families, on average, are poorer families. And arguably, they're poor because they're large, or they're large because they're poor. That correlation is hard to disentangle. But the simple problem here is that in Southeast Turkey, they have the largest families, i.e. they're also the poorest people in Southeast Turkey. So the vulnerabilities were already concentrated in that area before the earthquake happened. And on top of that, 6.5 million refugees from the decade of civil war in Syria, in this particular area. And poor people generally don't own the land they live in, or the land they live, don't own the land or the property that they live in. And they live in houses that are old or illegally built, and often in overcrowded conditions, which means they are more vulnerable to all shocks, not just earthquakes, tsunamis, or anything like that. They're vulnerable to all shocks, including a financial crisis or something like that. So this is a vulnerability of all kinds. And so if you find the poorest people, you will generally find the most vulnerable people in any community or any region around the world. So that's what we mean by social vulnerability. Corruption. And quite simply, this is again, I have another lecture on this. It's a really interesting topic. The misuse of entrusted power for private gain. And it doesn't take me to tell you that corruption is deadly. But how does it work in earthquakes? So the one form of corruption in earthquakes is using inadequate or insufficient building materials. So this is what some might call the golden ratio in engineering, is where you mix 1 bag cement with 3 bags sand, mix it with water, and that gives you a really strong mortar with which you can build your homes, and that's nice. But if you happen to be a corrupt contractor, cement is more expensive than sand. So if you're corrupt, you do this. You get 1 bag cement and 6 bags sand, and you pocket the money for that extra bag of cement you didn't use, and you mix it with water. It looks the same, it tastes the same, but that house does not behave the same because that mortar fundamentally not what it should be doing, isn't doing what it should be doing. Other forms of corruption is building houses in bad ways, i.e. cutting corners, not using the right following the right rules, not using the right materials. That happens a lot. And putting buildings in bad places. This is a problem all over the world. You need to look out to see how many houses there are in floodplains in the UK. This putting buildings in bad places is a big part of the sort of risk equation. And what happened in Turkey in 2023? So after some most major earthquakes, the get field investigation team that goes out to do some investigations, usually of engineers, to figure out what went wrong in that earthquake. So this earthquake engineering field investigation team went out to Southeast Turkey following the earthquake, and they took rock cores, but not through rock. They took it through the pillars of some of these big buildings that collapsed. And this is what they found in some of these buildings: some big rounded pebbles within the cement. And so those of you who are geologists know where big round pebbles come from. They come from rivers, right? So what this contractor had done to bulk out the cement, they went to the local river, got a load of stones, and just pumped it into this mortar that was going into this pillar. So that's corruption. That they just wanted to save money on aggregate, and fundamentally weakening that pillar, and arguably contributing to its collapse. Here's another form of corruption. So if you go outside and to a construction site, you'll see a lot of these rods, rebar rods, and rebar rods have very strict regulations of what kind of rebar rods you should use for what purpose. For pillars and those who are that are load bearing, you have to use pillars. You have to use rebar rods that have ridges on them, ribbed rebar rods. And what that does, the ridges increases the surface area between the cement and the rod, and thereby giving that good strong connection between the metal, which is the sort of the spine of the column, and the mortar around it. But ridged rebar is more expensive than smooth rebar. So if you're a corrupt contractor, what do? You buy a lot of smooth rebar, put it in the pillar, no one can see it, and you save a lot of money. But that fundamentally weakens that pillar, and again, arguably contributes to its collapse. And it's not like Turkey doesn't know what to do. Turkey has a very good and strict building code, and it updates it regularly. The last time it was updated was 2018, and they know how to build buildings because that's the Department of Engineering in the local university in Kahramanmaraş. So clearly, it's not about not knowing how to build buildings to withstand earthquakes. But as ever, and in every country, enforcement is the main challenge of those rules. So much so that this is a sales document from one of these big tower blocks that collapsed completely. And in Turkish, in the bit I've highlighted there, it says completed in compliance with the latest earthquake regulations. And of course it wasn't, and that's why it collapsed. And the owner or the builder of this building is now in I think he's in jail and waiting to be sentenced. But what if people did follow the rules? Here's a really interesting case study from Erzin, which is a district in the Hatay area, and it's very close to the earthquake. So remember, whereas Kahramanmaraş is this one here that nearly had 50% fatality. Erzin is further south here, not that far from the fault, probably about equidistance from the fault as Kahramanmaraş was, but there were no injuries in this town. No injuries, no buildings collapsed. I think a few chimneys fell off, but no buildings collapsed. And it's hard to decide, hard to say why that was the case, but this could be one of those reasons. The local mayor was well known for not allowing illegal construction and had a very good inspection process and got people to build things according to the rules. So maybe this was the main reason of why nobody died and nothing collapsed in Erzin. So following the rules does make a difference. Those rules are there for a reason. However, Turkey does have this incredible thing called imar barişi, which is a completely legal system to legalize buildings that were built illegally. And often it's used as a political thing to get votes. And before every election cycle, the president offers a legalization process where those old buildings that were built badly, they can pay a fine and they can get a certificate that says your home is now legal. The house or building is now legal. So nothing in the building changes. Nothing, no construction, no retrofitting will be done. You just get a certificate saying now this house is legal. And in Turkey, Southeast Turkey, around 300,000 buildings were legalized using this method before the earthquake in the 11 most affected provinces. And remember, this is completely legal. So this is legalized corruption. And I'm not sure what's happened since the earthquake, if this process is going, but I got that flyer online. I just had to Google it. So it's completely legal and a shocking thing. So corruption, how do you measure corruption? This turns out to be quite a hard thing to do because you can't actually objectively go to a country and say, how corrupt are you feeling today on a score of 0 to 10? But this group, Transparency International, does try and do that and integrates with all these surveys and many other measures that I don't have time to go into, and gives every country a score between 0 and 100. And in this case, 0 is absolutely corrupt, and a country that scores 100 is no corruption at all. And it won't surprise you to know that the least most corrupt countries in the world are in Scandinavia and New Zealand. And there's the sort of Scandinavian nations have done it again. And the most corrupt countries in the world, again, probably not surprising, are Somalia and Syria and Afghanistan and countries like North Korea and countries like that. And if I plot on here the 5 most deadly earthquakes in the last 30 odd years, they all fall in these orange and red countries, countries that are more corrupt than not. So think about this scale of 0 to 100. If you pick 50, that's the middle point on a corruption scale. That means you're not really corrupt, you're not really fully corrupt, not fully angelic, you're just the middle country. 2/3 of all countries in the world score below 50. That means they are more corrupt than not. So 2/3 of all countries in the world are more corrupt than not, according to this index. And why does that matter? It matters because the construction industry in those countries is the most corrupt segment of their economy. So the folks building the homes are the most corrupt people in those countries. According to, this is quite an old statistic from 2005, but I think it probably still holds. So Roger, I got one of my students to recreate and update this great figure from Nicholas and Bryce's and Roger Billen's 2012 paper that takes every country in the world and plots their national income, i.e. the GNI on the bottom, against the corruption index score on the y-axis. Remember, high scores are less corrupt and low scores are more corrupt. And it seems, and you can plot this with a pseudo trend line through this data set that more or less, and it's amazing that there's a trend at all. But what this trend line means is that if you fall on the line, you're just as corrupt as we expect you to be, given your national income. So countries like the United States, the UK fall on that line, more or less on the line. If you fall above the line, you're less corrupt than we expect you to be, given your national income. So countries like Japan, New Zealand, Chile fall above the line. If you fall below the line, you're more corrupt than we expect you to be, given your national income. Countries like Mexico, Russia, Iran, no surprises there. So to help us out, I've colored it in. Those are the good guys, those are the bad guys, and that's where it's all gone wrong. It's hard to disentangle all of these factors. And why does it matter? It matters because 83% of all deaths in the last 30 years were in low-income, corrupt nations. So corruption matters. Ignorance. What do I mean by that? This is also a problem of two parts. The first part of ignorance is knowledge gaps, i.e. knowledge of the world that we live in. Every now and then there's a big earthquake, and it always surprises us that there wasn't a fault line there. And here are two faults, two just papers that I've just pulled out of the Google Scholar of two big earthquakes that happen, two deadly earthquakes that happen on faults that were previously not identified. And this is the bread and butter of COMET. This is what our modus operandi is, to fill in these knowledge gaps, to understand the patterns of seismic around the world and where faults have been mapped and how you sort of increase that knowledge space. So this is what we need to do, keep doing, fill in the knowledge gaps of where it's dangerous and what sources of danger exist in the world to people. The other form of ignorance is this, which is, I think, is more nuanced and arguably more important. This is a graph of the number of students in the top left graduating from geological engineering degrees in Turkey. On the bottom, number of students graduating from geophysical engineering degrees in Turkey. And why is this a problem? Because they're all going down. It's all going down. And these are the two groups of people who know the problem and what to do about it. Right? So they know the geological problem, i.e. the geophysics and why it's dangerous, and the geophysical reasons why things are dangerous. And the engineering folks know what to do about it, how to fix it. And this decline is happening despite the fact the number of civil engineering courses remaining quite high. The number of courses on offer remain high, but the number of graduates coming are on a long-term decline. And this is a fundamental problem of talent and a future problem of having the right skills and talent in place to fix the problems that you have. And unfortunately, this is not a problem just in Turkey. This is a problem in the USA, in the UK, and most Western nations. So this type of long-term disaster risk, this is really, really concerning. So that was my four horsemen of disaster risk. And these have combined why an earthquake, or any hazard for that matter, relates to a disaster. However, next part of this talk is about this, cascading hazards. Because unfortunately, the real world isn't so simple as just an earthquake or a flood or a typhoon or whatever. They all interconnect into what we call multi-hazard cascades. And here's a very simple one that you will all be familiar with. Earthquakes can trigger tsunamis. That's a secondary cascading hazard. Earthquakes can trigger landslides. Those landslides can block rivers, and the rivers then flood. That's a very simple multi-hazard cascade. And here's a really good example of a real-world one. At the 2011 Tohoku earthquake, magnitude 9.1, you will all remember these shocking, or you will all have seen, hopefully, the shocking, powerful videos of the tsunami arriving. So that earthquake triggered a tsunami, triggered a big landslide. This particular landslide broke a dam that then flooded a village. And also, this natural hazard cascade connected to, as you will know, the explosion at the Fukushima power plant that led to a man-made disaster. So this is a complex natural man-made multi-hazard cascade. And these happen all the time everywhere in various different forms. So let's go back to Turkey and sort of look into the more detail around the multi-hazard cascades that followed that first earthquake. So we'll split the time in hours, weeks, and months, and the hazards into geological and hydrometeorological. And we'll start with that first earthquake, magnitude 7.8 at 4:17 in the morning. That triggered a small tsunami. I think it's about 14 centimeters high, but nonetheless a tsunami that still flooded part of the coastline in the south. And this 9 hours later, the second earthquake, I'll put an arrow there, not necessarily meaning it triggered it, but second earthquake happened. And again, both earthquakes triggered hundreds and hundreds of aftershocks that continued for many weeks and months following those two earthquakes. And liquefaction, quite prominent liquefaction in some areas that damaged a lot of sort of fields, mostly in this case, thankfully. And landslides, thousands of landslides. We've mapped at least 4,000, and I think some of my colleagues in Turkey have mapped up to 20,000 landslides following those earthquakes. And so remember, I said that first earthquake happened at 4:17 in the morning. What are most people doing at 4 a.m. in the morning? They're in bed, they're asleep, right? And they're asleep, and then the world starts shaking. And what do? You hopefully get under a table, hold on, and indeed the drop cover hold thing. And when it stops shaking, you run outside, right? That's the standard operating procedure of how to deal with an earthquake. So you run outside, wearing whatever you were wearing in bed. There's no time to pack a holiday luggage case. You run outside wearing whatever you were wearing outside in bed. And so what did these people run outside to? This: heavy snow, strong winds, and extreme cold. In some parts of Turkey, southeast Turkey at the time, the snow was 1 meter high. Winds were biting winter winds and minus 19 degrees Celsius in some parts of southeast Turkey at the time. So that's what people ran outside to. And then, of course, the snow and landslide interacted and led to slurry and mush and debris flows. And of course, the earthquake, the tsunami led to flooding. Liquefaction caused more flooding. The landslides will have led to flooding subsequently, but not in those immediate few hours. And then obviously then snow started to melt, so led to more sort of water issues. And that was all within a few hours to a few days of that main earthquake. A week later, now people are in tents. They're not allowed to be in their homes, they're in tents. And the last place you want to be when there's a severe storm that leads to more flash flooding. 20 people died in that event because they were in a tent, not in their homes. A week after that, again, another severe storm. This one led to flash floods again, a heavy hail, and a tornado. Heavy hail, when I say hail, it's not the things you get in the UK. These are like golf ball size hails that hit people. Fast forward again a few weeks. Now it's been a few months. Now it's summer, and people have been upgraded from tents to these metal containers from the shipping containers that more privacy, more safety, and a better security for an interim home. But the last place to be is when there's a 40-degree plus heat wave in a metal container. So that's the sort of multi-hazard cascade of just the first few months following that earthquake. And what were the impacts of this? Unsurprisingly, building collapse, disability, homelessness. We worry often about the people who've died and forget about the people who survived. And because they'll be homeless, there'll be injuries, there'll be psychosocial issues that need to be addressed, economic loss, of course, and in this particular case, the regional geopolitics came into play between Turkey and Syria. And thankfully, it worked out well, but Turkey and Syria were not on good terms before the earthquake. And that's really, it comes to mind if they remained not on good terms following the earthquake, which is probably what happened in Myanmar, which, again, another topic. And disrupted education. Nearly 4 million children were not in school for at least 2 months. We know very well from childhood psychology studies the impact of kids missing just a week of school has a long-term impact. 2.5 months of no school is a generational impact. So that needs to be accounted for and thought about and addressed. And this is what happened in February the 6th, 2023. If this system of events were to happen in February 6th, 2053, all of these hazards in red would be worse because of climate change. Climate change will exacerbate the impacts of many of these hazards. So time also matters. And here are some examples of what I meant by these multi-hazard cascades. And on the bottom, the snow. This is not snow. These are the hailstorm that hit a few weeks after. And this is the flood that killed 20 people living in tents. And so another sort of academic question I have is, when does the multi-hazard cascade end? I can still keep going with the hazard. There are many other hazards following the final heat wave on this list. Well, so where does it end? And also, how do you cluster these hazards? Is that one cluster that happened within a few hours of that event? Or is that one cluster there? Is the second one there that happened a few weeks later? Is that another cluster? And it's really hard to sort of say that's a mini cluster of cascading hazards, and that's another mini cluster, but the whole thing is part of one another big cascade. That we haven't got a consensus on how to sort of decide when the multi-hazard cascade has ended. A thing I might propose is that actually, because all of these events affect the same vulnerable group, maybe the recovery, the end, should be determined by the vulnerability of the people. Has the vulnerability recovered to what it was before the earthquake? And that in itself is difficult because it's impossible to measure it, and arguably it almost never recovers in some places. So this remains an open question, and I think it's an interesting and important question that we all need to address. So my cartoon of dynamic risk. Imagine a city on the coast, in any big city in the world, Jakarta, London, the cities are there partly because it's the coastline, and you get a big earthquake. This is my amazing clip art. And you have an earthquake, you go to the table, you hold on, and the shaking stops, you run outside, right? Great. If there's a big enough earthquake that's mainly to topple buildings, what should you do next? You should run uphill as fast as you can because you've got 15 minutes before that tsunami arrives. Up to 15, maybe 20 minutes. You run, right? Because that's what you should do. That's what you get taught in school because the tsunami arrives in 15 minutes. What about that person? There was one death in the Izmir earthquake in 2022. There was a small earthquake offshore, a moderate earthquake offshore that generated a small tsunami. One woman in a wheelchair died, not because from the earthquake, from the tsunami, because she couldn't wheel herself away from that tsunami quick enough. What about these people? Families, young people, elderly people, pregnant women. How do they run away from that tsunami? And think about this guy up there on the hill slopes. When it starts raining, what's going to happen to some of those hill slopes? Landslides. So this is what I mean by multi-hazard cascades. And actually, the vulnerability of each one of these people has changed because of the situation they're in and the time window that they're living in at the moment. So I'm saying is that changes in exposure and vulnerability during a multi-hazard scenario means your individualized risk evolves over time too. So risk becomes highly individual, depending on your condition and your circumstance during a multi-hazard crisis. So we need to rethink this age-old question, the age-old sort of equation. This is what the World Bank uses, this is all the UN. Everyone uses this model of disaster risk equals the hazard multiplied by the exposure multiplied by the vulnerability. And as you probably can get, we need to update this now, add time, because risk is time dependent. But I'm going to say, and make it a function of, because you never know actually how they will interact. But it's even more complicated than that because hazards, exposure, vulnerabilities, they all interact with each other because some hazards aren't actually always natural. Think about a hill slope that's been farmed. The landslide potential of that slope is very different to if it was a forested slope. Exposure and vulnerabilities, they all change with time. So they all interact with each other as well. And so the risk is highly dynamic as well in time and space. And each one of these components of that risk is also dynamic in time and space. And there's some examples of vulnerabilities changing in time. So this is the new model of what the risk equation could be. Problem is we can't turn it into an analytical function yet because it's quite complex, and I'm not smart enough to figure out how to do that. And so I think this is my last slide. So I've talked a little bit about this. It's quite gloomy about death and disasters and what makes a disaster. But I wanted to give you the context of it because this is the total number of fatalities that have happened in all natural hazards or disasters in the last century or so. And in around 1920s, on average, in 1 year, 500,000 people were dying in a disaster of some sort. And now it's around 50,000 people. And this dramatic decline is partly because we've gotten better at managing our vulnerabilities, particularly in this case for floods in what we call brown and droughts in purple. And so, what I'm saying is that we've been very good at reducing our risks to these particular hazards, But if you notice in this sort of, I don't know what the color is, greeny teal color, earthquakes are still quite damaging throughout time and non-uniform because they have a slightly different impact profile. The other thing I want to draw your eye to is this red, this increasingly worrying and increasing red column bar, and that's extreme temperatures. The number of people dying in extreme temperatures is on an increase, and that's a climate-driven process that we need to start thinking about how to address, particularly when it intersects with earthquakes and things like that, and other geophysical hazards that we know very well. So to summarize, the 2023 earthquake in Turkey was a tragic reminder of how poor planning and poor preparedness can compound with social and physical vulnerabilities and lead to that devastating impact that I showed you earlier. Disasters are fundamentally a human construct. We make disasters. If an earthquake happened in the middle of the Sahara Desert, it's not a disaster. It only becomes a disaster when it intersects with exposure, vulnerability, and corruption. Vulnerabilities can be spatially heterogeneous and temporal dynamic. They can change in space and time, and very quickly in some cases. So if you want to manage disaster risk, you not only need to understand the hazards, i.e. the geophysics, the thing that we do, but also the social and built environments that people live in. And disaster risk and planning, if you're a manager and planner for disaster risk, you need to think about the dynamic multi-hazard nature of risk and how you sort of manage against that. So you can't just manage the earthquake, you have to manage the earthquake-triggered floods, landslides, etc. And a warming world will exacerbate the vulnerabilities to all natural hazards. And I'll end it there. Thanks, guys.
Thank you so much, Ekbal. I'll give people a couple minutes if they want to put some comments in the Q&A. Yeah, I think it's really great that we're kind of opening up COMET to think about the wider picture of research in relation to disasters and natural hazards, and think about not just how we integrate Earth observation technologies and monitoring, but then how we think about the people and the impacts of such on them. So yeah, I can't see the Q&A, so I'm going to pass it across to Ben and Jen, but hopefully there's some questions there, and if not, I'm sure we can come up with some.
Don't need to ask questions.
Yeah, I mean, we haven't got any questions in just yet, but whilst we're waiting, I had one, which is kind of on the vulnerability side of things. You were discussing about how a lot of the impacts are coming from people building new buildings inadequately. But I was wondering, almost like flipping that around, how much of that, well, because you mentioned the regulations that came in 2018. Obviously, a lot of buildings were built before 2018. I don't know what the regulations were like before that, but how much of an issue is it like retrofitting or upgrading buildings when we didn't have the knowledge to do it or the regulations?
Retrofitting is expensive. And it also depends what kind of retrofitting we do. It can be quite expensive. There are cheaper options and alternatives that do get implemented. A really good example is in Nepal. They've got some really clever retrofitting examples, but it can be quite expensive. In some countries, you often wait for the life cycle of that building to just naturally get to an end, and they replace it with a better building. Most buildings have a life cycle, and we might not realize that. I think it's around 30 to 50 years. Most buildings will get replaced in some form or another. And so often it's cheaper to wait. But example in Turkey, they've had a pretty good regulation for quite a long time. And before many of these buildings would have been built, actually. And so, even if you built to the last code, you still would have been pretty safe. Each code is a minor tweak. But they started doing it decades and decades ago, building these codes together. And the big one was after that 99 earthquake. But earthquakes aren't new in Turkey. They've known about this for centuries and millennia, and so they've had time to think about what works and what doesn't work in their context. It's the enforcement of them that's always a problem, regardless of how good the rules are. It helps no one if they're not enforced, and that's a challenge every country in the world. It's not just Turkey.
Yeah. Thank you very much. We do have one question in now from Matthew Cleve, which is, great talk, Ekbal. Thank you. From your experience, what is the best way to communicate these risks to vulnerable people? Is it best to educate the people or the governments?
Thanks, Matt. I I'm personally, this is again personal perspective, I'm not a huge fan of directly communicating risks to local communities. I think it's better to always go work with local partners and work with locals, agencies, local people, sort of scientists and or community members who understand and work with as an intermediary, partly because communicating these things requires knowledge of local culture. I think culture is such an important part of how we absorb information and how we disseminate information, how we even trust information. And so I think understanding that culture you are working with and working with that culture rather than trying to fly in and say, this is what your risk is. So, for example, really good examples are in Indonesia. I'm doing a lot of work in Indonesia in recent years. In some parts of Indonesia, particularly in some of these volcanoes, they don't trust the scientists. They trust their local religious leaders or the sort of spiritual leaders. And so the best way to communicate in those communities is not to go directly to the communities, to work with the spiritual leaders and the groups that get trusted. And I think that is a good model in general to work in communities. We've got a really interesting project at the moment in West Java, working with communities and designing disaster resilience plans for local communities. But actually, I've not done any of it. I just get the updates because it's something for me to do. It's for my local partners to go out there and talk to those communities, and I can lead a project, but I think those things are best done by those local teams that you have.
Great, thank you very much. That was it for the questions for today, unless there's any from any more coming in last minute chats.
Okay.
Sorry, in the Q&A or any from Erin or Jin.
I haven't heard this talk before, so it's okay.
I can ask the same questions as before if you wish.
It's okay.
Well, we might just call it there then if everyone's happy with that. Thank you so much, everyone, for joining. We will have another webinar at the end of February. Please do join us then. And this recording should be made online. So hopefully if you've got any other questions, you can go back and have a listen again. So thank you so much, everyone, and we'll see you soon. Thank you again, Ekbal.
No worries.
As always, thank you, and we'll see you all soon.
Cheers, guys. Bye-bye.